Go.
Hello everyone. For today we're gonna discuss is all about memory management requirements. While surveying the various mechanisms and policies associated with memory management, it is helpful to keep in mind the requirements that memory management is intended to satisfy. These requirements include the following: relocation, protection, sharing, logical organization, and physical organization. Relocation multi-programming system, the available main memory is generally shared among a number of processes. Typically, it is not possible for the programmer to know in advance which other programs will be resident in main memory at the time of execution of his or her program. In addition, we would like to be able to swap active processes in and out of main memory to maximize processor utilization by providing a large pool of ready processes to execute. Once a program is swapped out to disk, it would be quite limiting to specify that when it next swap back, it must be placed in the same main memory region as before. Instead, we may need to relocate the process to a different area of main memory. Protection. Each process should be protected against unwanted interference by other processes, whether accidental or intentional. Thus, programs in other processes should not be able to reference memory locations in a process for reading or writing purposes without permission. In one sense, satisfaction of the relocation requirement increases the reading. In one sense, satisfaction of the relocation requirements increases the difficulty of satisfying the protection requirement because the location of a program in main memory is unpredictable. It is impossible to check absolute addresses at compile time to assure protection. Furthermore, most programming languages allow the dynamic calculation of addresses at runtime. Example, by computing an array subscript or a pointer into a data structure. Hence, all memory reference generated by a process must be checked at runtime to ensure they refer only to the memory space allocated to that process. Fortunately, we should see that mechanisms that support relocation also support the protection requirement. Normally, a user process cannot access any portion of the operating system, neither program nor data. Again, usually program in one process cannot branch to an instruction in another process. Without special arrangement, a program in one process cannot access the data area of access.
Sharing. Any protection mechanisms must have the flexibility to allow several processes to access the same portion of main memory. For example, if a number of processes are executing the same program, it is advantageous to allow each process to access the same copy to the program rather than have its own separate copy. Processes that are cooperate on some tasks may need to share access to same data structure. The memory management system must therefore allow controlled access to shared areas of memory without compromising essential protection. Again, we will see that mechanisms used to support relocation also support sharing capabilities.
Logical organization. Almost invariably, main memory in a computer system is organized as a linear or one-dimensional address space consisting of a sequence of bytes or words. Secondary memory at its physical level is similarly organized, while this organization closely mirrors that actual machine hardware. It does not correspond to the way in which programs are typically constructed. Most programs are organized into modules, some of which are unmodifiable, read-only, exit-only, and some of which contain data that may be modified. If the operating system and computer hardware can effectively deal with user programs and data in the form of modules of some sort, then a number of advantages can be realized. First, modules can be written and compiled independently, with all references from one module to another system at runtime. Second, with modest additional overhead, different degrees of protection, read-only, execute-only, can be given to the different modules. It is possible to introduce mechanisms by which modules can be shared among processes. The advantage of providing sharing on a module level is that this corresponds to the user's way of viewing the problem. Hence, it is easy for the user to specify the sharing that is desired.
Physical organization. As we discussed in section 1.5, computer memory is organized into at least two levels referred to as a main memory and secondary memory. Main memory provides fast access to relatively high cost. In addition, main memory is volatile, that is, it does not provide permanent storage. Secondary memory is slower and cheaper than main memory, but is usually not volatile. Thus, secondary memory of large capacity can be provided for long-term storage for programs and data, while a smaller main memory holds programs and data currently in use. In this two-level scheme, the organization of the flow and information between main and secondary memory is a major system concern. The responsibility for these flows could be assigned to the individual programmer, but this is impractical and undesirable for two reasons. One, the main memory available for program and its data may be insufficient. In that case, the program must engage in a practice known as overlaying, in which the program and data are organized in such a way that various modules can be assigned the same region of memory, with a main program responsible for switching and at the module in out as needed. Of compiler tools. Overlay programming. Programming wastes programming time. 2.
In a multi-programming.
In a multi-programming environment, the programmer does not know at the time of coding how much place will be available or where the space will be.
For 7.2, memory partitioning. The principal operation of memory management is to bring processes into main memory for execution by the processor. In almost all modern multi-programming systems, this involves a sophisticated scheme known as virtual memory.
Fixed partitioning. In most schemes for memory management, we can assume the OS or operating system occupies some fixed portion of main memory, and the rest of main memory is available for use by multiple processes. The simplest scheme for managing this available memory is to partition into region with fixed boundaries. Partition sizes. There are two difficulties with the use of equal size fixed partitions. Figure 7.2. Show examples of two alternatives for fixed partitioning. One possibility is to make use of equal size partitions. In this case, any process whose size is less than or equal to the partition size can be loaded into any available partitions. If all partitions are full and no process in this in is the ready for running state the operating system
Okay.
can swap a process out of any of the partitions and load in another process. So there is some work for the processor.
A program may be too big to fit into a partition. In this case, the programmer must design the program with the use of overlays, so only a portion of the program need be in main memory at any one time. When a module is needed that is not present, the user's program must load that module into the program's partition, overlaying whatever programs or data are there. Main memory utilization is extremely inefficient. Any program, no matter how small, occupies an entire partition. In our example, there may be a program whose length is less than 2 MB, yet it occupies an 8 MB partition whenever it is swapped in. This phenomenon in which there is wasted space internal to a partition due to the fact that the block of data loaded is smaller than the partition is referred to as internal fragmentation. Placement algorithm. With equal size partitions, the placement of processes in memory is trivial. As long as there is any available partition, a process can be loaded into the partition because all partitions are of equal size. It does not matter which partition is used if all partitions are occupied with processes that are not ready to run. Then one of these processes must be swapped out to make room for a new process. Which one to swap out is scheduling decision. This topic will be explored in part 4. With unequal size partition, there are two possible ways to assign processes to partitions.
See Figure 7.3a. The advantage of this approach is that processes are always assigned in such a way as to minimize wasted memory within a partition. Internal fragmentation. First, this assumes one knows the maximum amount of memory that a process will require. This is not always the case if it is not known how large a process may become. The only alternatives are an overlay scheme or the use of virtual memory. Dynamic partitioning. To overcome some of the difficulties with fixed partitioning, an approach known as dynamic partitioning was developed. Again, this approach has been supplanted by more sophisticated memory management techniques. An important operating system that used this technique was IBM's Mainframe Operating System, OS/MVT, or multi-programming with a variable number of tasks. With dynamic partitioning, the partitions are of variable length and number when a process is brought into main memory. It is allocated number when a process is brought into main memory. It is called it is allocated exactly as much memory as it requires and no more. An example, using 64 MB of main memory is shown in figure 7.4. Initially, main memory is empty, except for the OS. See figure 7.4a. The first three processes are loaded in, starting when the operating system ends and occupying just enough space for each process. See figure 7.4 B, C, D. This leaves us this leaves a hole at the end of memory that is too small for a fourth process. At some point, none of the processes in memory is ready. The operating system swaps out process 2. See figure 7.4e. which leaves sufficient room to load a new process, process 4, see figure 7.4f, because process 4 is smaller than process 2. Another small hole is created. Later, a point is reached at which none of the process in main memory is ready, but process 2 in the ready suspend state is available because there is sufficient room in memory for process 2. The operating system swaps process 1 out, see figure 7.4g, and swaps process 2 back in see figure 7.4h. Placement algorithm. Because memory compaction is time-consuming, the OS designer must be clever in deciding how to assign processes to memory, how to plug the holes when it is time to load or swap a process into main memory, and if there is more than one free block of memory of sufficient size, then the operating system must decide which free block to allocate. Three placement algorithms that might be considered are best fit, first fit, and next fit. All, of course, are limited to choosing among three blocks of main memory that are equal to or larger than the process to be brought in. Best fit chooses the block that is closest in size to the request. First fit begins to scan memory from the beginning and chooses the first available block that is large enough. Next fit begins to scan memory from the location of the last placement and chooses the next available block that is large enough. Figure 7.5b shows the difference between the best first and next fit placement algorithms in satisfying a 16 MB allocation request. Best fit will research the entire list of available blocks and make use of the 18 MB block, leaving a 2 MB fragment. First fit results in 6 MB fragment, and next fit results in a 20 MB fragment. Body system, both fixed and dynamic partitioning scheme have drawbacks. A fixed partitioning scheme limits the number of active processes and may use space inefficiently if there is a poor match between available partition sizes and process sizes. A dynamic partitioning scheme is more complex to maintain and includes the overhead of compaction. Uninteresting compromise is the body system. Figure 7.6 gives an example using a 1 byte initial block. The first request A is for 100 kbytes, for which a 128K block is needed. The initial block is divided into two 512K bodies. The first of this is divided into two 256K bodies, and the first of this is divided into two 128K bodies, one of which is allocated to A. The next request B requires a 256K block. Such a block is already available and is allocated. The process continues with splitting and coalescing occurring as needed. Note that when E is released, two 128K bodies are coalesced. 128K bodies are coalesced into a 256K block, which is immediately coalesced with its body. Figure 7.7 Figure 7.7 shows a binary tree representation of the body allocation immediately after the release B request. The left nodes represent the current partitioning of the memory. If two bodies are left nodes, then at least one must be allocated. Otherwise, they would be coalesced into a larger block. Figure 7.8 shows the way in which this address translation is typically accomplished. When a process is assigned to the running state, special processor register, sometimes called the base register, is loaded with the starting address and main memory of the program. There is also a bound register that indicates the ending location of the program. These values must be set when the program is loaded into memory or when the processor image is swapped in. during the course of execution of the process. Relative addresses are encountered. These include the contents of the instruction register. Instruction address Instruction addresses that occur in branch and call instructions, and data addresses that occur in load and store instructions. Each SAS relative address goes through two steps of manipulation by the processor. First, the value in the base register is added to the relative address to produce an absolute address. Second, the resulting address is compared to the value in the bounds register. If the address is within bounds, then the instruction execution may proceed. Otherwise, an interrupt is generated to the operating system, which must respond to the error in some fashion. 7.3 Paging. Both unequal fixed size and variable size partitions are inefficient in the use of memory. The former results in internal fragmentation, the latter in external fragmentation. Suppose, however, main memory is partitioned into equal fixed size chunks that are relatively small, and each process is also divided into small fixed size chunks of the same size. Then the chunks of a process known as pages could be assigned to available chunks of memory, known as frames or page frames. We show in this section that the wasted space in the memory for each process is due to internal fragmentation, consisting of only a fraction of the large page of a process. There is no external fragmentation. Figure 7.9 illustrates the use of pages and frames. At a given point in time, some of the frames in memory are used and some are free. A list of free frames is maintained by the OS. Process A, stored on disk, consists of 4 pages. When it is time to load this process, the OS finds 4 free frames and loads the Process B, consisting of 3 pages, and Process C, consisting of 4 pages, are subsequently loaded. Then Process B is suspended and is swapped out of main memory. Later, all of the processes in main memory are blocked, and the OS needs to bring in a new process, Process D, which consists of 5 pages. 7.4 It is segmentation. A user program can be subdivided using segmentation, in which the program and its associated data are divided into a number of segments. It is not required that all segments of all programs be of the same length, although there is a maximum segment length. As with paging, a logical address using segmentation consists of two parts, in this case a segment number and an offset, because of the use of unequal size segments. Segmentation is similar to dynamic partitioning. In the absence of an overlay scheme or the use of virtual memory, it would be required that all of the program segments be loaded into memory for execution. The difference compared to dynamic partitioning is that with segmentation, a program may occupy more than one partitioning and their partitions need not be contiguous. Segmentation eliminates internal fragmentation, but like dynamic partitioning, it suffers from external fragmentation. However, because a process is broken up into a number of smaller pieces, the external fragmentation should be less. Whereas paging is invisible to the programmer, segmentation is usually visible and is provided as a convenience for organizing programs and data. Typically, the program or compiler will assign programs and data to different segments for of modular program purposes of modular process, the program or data may be further broken down into multiple segments. The process The program inconvenience of this service is that the programmer must be aware of the maximized size limitation. Another consequence of unequal size segments is that there is no simple relationship between logical addresses and physical addresses. Analogs to paging, a simple segmentation would make use of a segment table for each process and a list of pre-blocks of main memory. Each segment table entry would have to give the starting address in main memory of the corresponding segment. The entry should also provide the length of the segment to assure that invalid addresses are not used. When a process enters the running state, the address of each segment table is into a special register used by the memory management hardware. Consider an address of bits where the leftmost in bits are the segment number and the rightmost in bits are the offset. In our example, see figure 7.11c, and thus the maximum segment size is the following steps are needed for address translation. Extract the segment number as the leftmost in bits of the logical address. Use the segment number as an index into the process segments table to find the starting physical address of the segment. Compare the offset expressed in the rightmost in bits to the length of the segment. If the offset is greater than or equal to the length, the address is invalid. The desired physical address is the sum of the starting physical address of the plus the offset. And 7.5 summary at last, one of the most important and complex tasks of an operating system is memory management. Memory management involves treating main memory as a resource to be allocated to and shared among a number of active processes. To use the processor and the I/O facilities efficiently, it is desirable to maintain as many processes in main memory as possible. In addition, it is desirable to free programmers from size restrictions in program development. The basic tools of memory management are paging and segmentation. With paging, each process is divided into a relative small, fixed-size pages. Segmentation provides for the use of pieces of varying size. It is also possible to combine segmentation and paging in a single memory management scheme. And that's all for today. Thank you for watching me. Goodbye.